Hello everyone, I am Gaygin Karanyan, I am teacher of physics, and in this video I will discuss several problems connected with gravitational field. The first of all, let's define Newton's law of gravity, which is the force between two masses and which is equal to gravitation constant g times the mass of the first object times the mass of the second object divided by the distance squared between the two objects. And g is the gravitation constant, as I have said, and which is equal to 6.67 applied to 10 minus 11 Newton meter square and divided by kilogram square. M1 and M2 are the masses of the objects, and R is distance between center of object masses. Now let's discuss physics problems which we will try to solve using the Newton's law of gravity in no standard situation. Problem 1, we should prove that the gravitational field of a spherical layer, homogeneous in density, is absent inside the sphere surrounded by this layer. And at first, I will use physical and mathematical standard formulas to solve this problem. Then the same problem I will try to solve at a qualitative level using the methodological principle of symmetry. And generally, to solve this problem, we can use mathematical formulas. Then let's take spherical layer with small thickness, put at a probe arbitrary point M inside the spherical layer. We will highlight S1 area on the layer, then create a cone topping the point of the M and the base of S1. Let's continue cone till the intersection with another side of the layer, which we label as S2. We will take S1 and S2 particles so small that in comparison with M we can define S1 and S2 as a point masses, and then we can see that S1 and S2 act on the M point with F1 and F2 forces, and we can see and we'll mention that these forces have opposite direction. In these formulas, M1 and M2 are masses of particle S1 and S2, R1 and R2 are distance of M from the particles, and it's easy to make sure that these two cones are similar to each other, from which we can write that S1 divided by S2 is equal to R1 divided R2 square, from which we can find M1 divided by F2, which is finally equal to R1 divided by R2 square. From formula 1 and 2, we can find that F1 is equal to F2. That is, the net force of M mass and M1 and M2 interaction is equal to 0. However, we can divide all spherical layers into pair of elements. Let's divide it. Elements. And which have these characteristics. The interaction force of M acting on layer is equal to 0 and don't depend on the position of M inside the layer. And therefore, field inside the layer is absent, which should be proved. Here is the second way of the solution, which is based only on qualitative observations using methodological principle of symmetry, and in this case there is no need for any mathematical modeling. Unlike other geometrical bodies, sphere has spherical symmetry. It is symmetric both to its center and any line passing through the center. That means if force line of gravitational field exists inside of the sphere, therefore they must be centralized. Totally spherical symmetry are only the rays which come out from the center of O and in various directions, and they make the straight lines of the field which intersect in O point. And as it is known that the straight line can be intersected in anywhere where is no mass, As it was mentioned in the problem above, there is no mass inside. We know, and the gravitational field is absent inside of the sphere, which should be proved. Thereby, we observed two ways of solution, one of which was quite long, as we have seen, and in the result of using mathematical formulas, and this other one was short, based only on quantitative observations. Now let's discuss the second problem, and we should create a schedule of the magnitude dependency of acceleration of free fall g in the gravitational field created with homogeneous sphere from the distance to the center of the sphere. In solution 1, it is known that the homogeneous sphere outside of it creates such gravitational field as the whole mass is focused in the center. In this way, the acceleration is changing outside of the sphere according to this law. Gx is equal to gm divided by x2, x greater or equal to r, where m is the mass of the sphere, x is the distance to its center. We put point probe mass to the point A on distance of x from the center, where x smaller than r. The pore of intersection of the mass with a spherical layer is equal to 0, which inner radius is equal to x. And therefore, the interaction force of probe mass with the whole sphere is the same, as the spherical layer didn't exist at all. That is the acceleration of the point A. And gx is equal to gmx divided by x square, where x smaller or equal to r, where mx is the mass of the sphere with the x radius, that is the mx is equal to mx cubed divided by r cubed. And to put this in the formula 1, we can get the following formula. Gx finally is equal to g0x divided by r, x smaller than or equal to r, that is the acceleration inside of the sphere, which is changing directly proportional to distance of the center of the sphere, which should shown. And magnitude of the g0 is the acceleration of the gravitational force on the surface of the sphere. Meanwhile, we see that g0 is equal to gm divided by r, and graph of dependency g from x of the center. And now the wanted result as a whole is can be easily got using the Gauss law. Let's discuss the second solution. And it is obvious that the field of the homogeneous sphere has a spherical symmetry, whereas the tension of the field is always directed along the line connecting the sphere with the center. Let's take the surface of the sphere center x radius, the flow of tension through that surface, and we can write the law of Gauss. Px is equal to 4px squared g x, and according to the Gauss law we can write the second formulas, and then we can consequently find the gx and third formulas. As we see, we can solve this problem in a very short way without using long mathematical formulas. And that's all. Thank you for your attention.